the International Space Station is a space station, or a habitable artificial satellite, in low Earth orbit. It is a modular structure whose first component was launched in 1998. Now the largest artificial body in orbit, it can often be seen at the appropriate time with the naked eye from Earth. The island consists of pressurized modules, external trusses, solar arrays and other components. ISS components have been launched by American Space Shuttles as well as Russian Proton and Soyuz rockets. In 1984, the ESA was invited to participate in Space Station Freedom. After the USSR dissolved, the United States and Russia merged Mir-2 and Freedom together in 1993. The island serves as a microgravity and space environment research laboratory in which crew members conduct experiments in biology, human biology, physics, astronomy, meteorology and other fields. The station is suited for the testing of spacecraft systems and equipment required for missions to the Moon and Mars. Since the arrival of Expedition 1 on November 2, 2000, the station has been continuously occupied for 700113000000013 years and 70022580000000258 days, the longest continuous human presence in space. Held by Mir. The station is serviced by a variety of visiting spacecraft: Soyuz, Progress, the Automated Transfer Vehicle, the HII Transfer Vehicle, Dragon, and Cygnus. It has been visited by astronauts and cosmonauts from 15 different nations. After the U.S. Space Shuttle program ended in 2011, Soyuz rockets became the only provider of the transport for astronauts at the International Space Station, while Dragon became the only provider of cargo return-to-Earth services. The island's program is a joint project among 5 participating space agencies: NASA, Roscosmos, JAXA, ESA, and CSA. The ownership and use of the space station is established by intergovernmental treaties and agreements. The station is divided into 2 sections, the Russian orbital segment and the United States orbital segment, which is shared by many nations. The island maintains an orbit with an altitude of between 330 km and 435 km by means of reboost maneuvers using the engines of the Zvezda module or visiting spacecraft. It completes 15.50 in orbits per day. The island is funded until 2024, and may operate until 2028. The Russian Federal Space Agency, Roscosmos, has proposed using the ISS to commission modules for a new space station, called OPSEK, before the remainder of the ISS is deorbited. ISS is the 9th space station to be inhabited by crews, following the Soviet and later Russian Salyut, Almaz, and Mir stations, and Skylab from the U.S. Purpose. According to the original Memorandum of Understanding between NASA and Rosavia-Cosmos, the International Space Station was intended to be a laboratory, observatory and factory in space. It was also planned to provide transportation, maintenance, and act as a staging base for possible future missions to the Moon, Mars and asteroids. In the 2010 United States National Space Policy, the ISS was given additional roles of serving commercial, diplomatic and educational purposes. Scientific research. The islands provides a platform to conduct scientific research that cannot be performed in any other way. While small unmanned spacecraft can provide platforms for zero gravity and exposure to space, space stations offer a long-term environment where studies can be performed potentially for decades, combined with ready access by human researchers over periods that exceed the capabilities of manned spacecraft. The station simplifies individual experiments by eliminating the need for separate rocket launches and research staff. The wide variety of research fields include astrobiology, astronomy, human research including space medicine and life sciences, physical sciences, materials science, space weather, and weather on Earth. Scientists on Earth have access to the crew's data and can modify experiments or launch new ones, which are benefits generally unavailable on unmanned spacecraft. Crews fly expeditions of several months' duration, providing approximately 160 man-hours a week of labor with a crew of 6. Cuba is intended to accelerate Japan's progress in science and technology, gain new knowledge and apply it to such fields as industry and medicine. To detect dark matter and answer other fundamental questions about our universe, engineers and scientists from all over the world built the Alpha Magnetic Spectrometer, which NASA compares to the Hubble telescope, and says could not be accommodated on a free-flying satellite platform due in part to its power requirements and data bandwidth needs. On April 3, 2013, NASA scientists reported that hints of dark matter may have been detected by the Alpha Magnetic Spectrometer. According to the scientists, the first results from the spaceborne Alpha Magnetic Spectrometer confirm an unexplained excess of high-energy positrons in Earth-bound cosmic rays. The space environment is hostile to life. Unprotected presence in space is characterized by an intense radiation field, high vacuum, extreme temperatures, and microgravity. Some simple forms of life called extremophiles, including small invertebrates called tardigrades, can survive in this environment in an extremely dry state called desiccation. Medical research improves knowledge about the effects of long-term space exposure on the human body, including muscle atrophy, bone loss, and fluid shift. This data will be used to determine whether lengthy human spaceflight and space colonization are feasible. As of 2006, data on bone loss and muscular atrophy suggest that there would be a significant risk of fractures and movement problems if astronauts landed on a planet after a lengthy interplanetary cruise, such as the 6-month interval required to travel to Mars. Medical studies are conducted aboard the ISS on behalf of the National Space Biomedical Research Institute. Prominent among these is the Advanced Diagnostic Ultrasound in Microgravity study, in which astronauts perform ultrasound scans under the guidance of remote experts. The study considers the diagnosis and treatment of medical conditions in space. Usually, there is no physician on board the ISS, and diagnosis of medical conditions is a challenge. It is anticipated that remotely guided ultrasound scans will have application on Earth in emergency and rural care situations where access to a trained physician is difficult. Microgravity. The Earth's gravity is only slightly weaker at the altitude of the ISS than at the surface. However, objects in orbit are in a continuous state of freefall, resulting in an apparent state of weightlessness. This perceived weightlessness is disturbed by 5 separate effects. Drag from the residual atmosphere. When the ISS enters the Earth's shadow, the main solar panels are rotated to minimize this aerodynamic drag, helping reduce orbital decay. Vibration from movements of mechanical systems and the crew. Actuation of the onboard attitude control moment gyroscopes. Thruster firings for attitude or orbital changes. Gravity gradient effects, also known as tidal effects. Items at different locations within the ISS would, if not attached to the station, follow slightly different orbits. Being mechanically interconnected, however, these items experience small forces that keep the station moving as a rigid body. Researchers are investigating the effect of the station's near-weightless environment on the evolution, development, growth and internal processes of plants and animals. In response to some of this data, NASA wants to investigate microgravity's effects on the growth of 3-dimensional, human-like tissues, and the unusual protein crystals that can be formed in space. The investigation of the physics of fluids in microgravity will allow researchers to model the behavior of fluids better. Because fluids can be almost completely combined in microgravity, physicists investigate fluids that do not mix well on Earth. In addition, an examination of reactions that are slowed by low gravity and temperatures will give scientists a deeper understanding of superconductivity. The study of materials science is an important ISS research activity, with the objective of reaping economic benefits through the improvement of techniques used on the ground. Other areas of interest include the effect of the low-gravity environment on combustion, through the study of the efficiency of burning and control of emissions and pollutants. These findings may improve current knowledge about energy production, and lead to economic and environmental benefits. Future plans are for the researchers aboard the ISS to examine aerosols, ozone, water vapor, and oxides in Earth's atmosphere, as well as cosmic rays, cosmic dust, antimatter, and dark matter in the universe. Exploration. The islands provides a location in the relative safety of low Earth orbit to test spacecraft systems that will be required for long-duration missions to the Moon and Mars. This provides experience in operations, maintenance as well as repair and replacement activities on orbit, which will be essential skills in operating spacecraft farther from Earth. Mission risks can be reduced and the capabilities of interplanetary spacecraft advanced. Referring to the Mars 500 experiment, ESA states that whereas the ISS is essential for answering questions concerning the possible impact of weightlessness, radiation and other space-specific factors, aspects such as the effect of long-term isolation and confinement can be more appropriately addressed via ground-based simulations. Sergei Krasnov, the head of human spaceflight programs for Russia's space agency, Roscosmos, in 2011 suggested a shorter version of Mars 500 may be carried out on the ISS. In 2009, noting the value of the partnership framework itself, Sergei Krasnov wrote, "When compared with partners acting separately, partners developing complementary abilities and resources could give us much more assurance of the success and safety of space exploration." The islands is helping further advance near-Earth space exploration and realization of prospective programs of research and exploration of the Solar System, including the Moon and Mars. A manned mission to Mars, however, may be a multinational effort involving space agencies and countries outside the current ISS partnership. In 2010, ESA Director General Jean-Jacques Dordain stated his agency was ready to propose to the other four partners that China, India and South Korea be invited to join the ISS partnership. NASA Chief Charlie Bolden stated in February 2011 any mission to Mars is likely to be a global effort. Currently, American legislation prevents NASA cooperation with China on space projects. Education and cultural outreach. The Islands Group provides opportunities for students on Earth by running student-developed experiments, making educational demonstrations, allowing for student participation in classroom versions of ISS experiments, and directly engaging students using radio, video link and email. ESA offers a wide range of free teaching materials that can be downloaded for use in classrooms. In one lesson, students can navigate a 3D model of the interior and exterior of the ISS, and face spontaneous challenges to solve in real time. JAXA aims both to stimulate the curiosity of children, cultivating their spirits, and encouraging their passion to pursue craftsmanship, and to heighten the child's awareness of the importance of life and their responsibilities in society. Through a series of education guides, a deeper understanding of the past and near-term future of manned space flight, as well as that of Earth and life, will be learned. In the JAXA Seeds and Space Experiments, the mutation effects of spaceflight on plant seeds aboard the ISS is explored. Students grow sunflower seeds which flew on the ISS for about 9 months as a start to touch the universe. In the first phase of Cuba utilization from 2008 to mid-2010, researchers from more than a dozen Japanese universities conducted experiments in diverse fields. Cultural activities are another major objective. Tetsuo Tanaka, Director of JAXA's Space Environment and Utilization Center, says there is something about space that touches even people who are not interested in science. Amateur Radio on the ISS is a volunteer program which encourages students worldwide to pursue careers in science, technology, engineering and mathematics through amateur radio communications opportunities with the ISS crew. ARISS is an international working group, consisting of delegations from 9 countries including several countries in Europe as well as Japan, Russia, Canada, and the United States. In areas where radio equipment cannot be used, speakerphones connect students to ground stations which then connect the calls to the station. First Orbit is a feature-length documentary film about Vostok 1, the first manned space flight around the Earth. By matching the orbit of the International Space Station to that of Vostok 1 as closely as possible, in terms of ground path and time of day, documentary filmmaker Christopher Riley and ESA astronaut Paolo Nespoli were able to film the view that Yuri Gagarin saw on his pioneering orbital spaceflight. This new footage was cut together with the original Vostok 1 mission audio recordings sourced from the Russian State Archive. Nespoli, during Expedition 26/27, filmed the majority of the footage for this documentary film, and as a result is credited as its director of photography. The film was streamed through the website firstorbit.org in a global YouTube premiere in 2011, under a free license. In May 2013, Commander Chris Hadfield shot a music video of David Bowie's Space Oddity on board the station. The film was released freely on YouTube. It was the first music video ever to be filmed in space. Origins. History. The assembly of the International Space Station, a major endeavor in space architecture, began in November 1998. Russian modules launched and docked robotically, with the exception of Rassvet. All other modules were delivered by the Space Shuttle, which required installation by ISS and shuttle crew members using the SSRMS and EVAs. As of June 5, 2011, they had added 159 components during more than 1,000 hours of EVA. 127 of these spacewalks originated from the station, while the remaining 32 were launched from the airlocks of docked space shuttles. The beta angle of the station had to be considered at all times during construction, as the station's beta angle is directly related to the percentage of its orbit that the station is exposed to the Sun. The Space Shuttle would not perform optimally above a limit called the beta cutoff. The first module of the ISS, Zarya, was launched on November 20, 1998 on an autonomous Russian Proton rocket. It provided propulsion, attitude control, communications, electrical power, but lacked long-term life support functions. 2 weeks later a passive NASA module Unity was launched aboard Space Shuttle Flight STS-88 and attached to Zarya by astronauts during EVAs. This module has two pressurized mating adapters, one connects permanently to Zarya, the other allows the Space Shuttle to dock to the space station. At this time, the Russian station Mir was still inhabited. The islands remained unmanned for 2 years, during which time Mir was deorbited. On July 12, 2000 Zvezda was launched into orbit. Pre-programmed commands on board deployed its solar arrays and communications antenna. It then became the passive vehicle for a rendezvous with the Zarya and Unity. As a passive target vehicle, the Zvezda maintained a station-keeping orbit as the Zarya Unity vehicle performed the rendezvous and docking via ground control in the Russian automated rendezvous and docking system. Zarya's computer transferred control of the station to Zvezda's computers soon after docking. Zvezda added sleeping quarters, a toilet, kitchen, CO2 scrubbers, dehumidifier, oxygen generators, exercise equipment, plus data, voice and television communications with mission control. This enabled permanent habitation of the station. The first resident crew, Expedition 1, arrived in November 2000 on Soyuz TM-31. At the end of the first day on the station, astronaut Bill Shepard requested the use of the radio call sign Alpha, which he and cosmonaut Krykalev preferred to the more cumbersome International Space Station. The name Alpha had previously been used for the station in the early 1990s, and following the request, its use was authorized for the whole of Expedition 1. Shepard had been advocating the use of a new name to project managers for some time. Referencing a naval tradition in a pre-launch news conference he had said, "For thousands of years, humans have been going to sea in ships. People have designed and built these vessels, launched them with a good feeling that a name will bring good fortune to the crew and success to their voyage." Yuri Semenov, the president of Russian Space Corporation Energia at the time, disapproved of the name Alpha. He felt that Mir was the first space station, and so he would have preferred the names Beta, or Mir-2 for the ISS. Expedition 1 arrived midway between the flights of STS-92 and STS-97. These two space shuttle flights each added segments of the station's integrated truss structure, which provided the station with Ku-band communication for U.S. television, additional attitude support needed for the additional mass of the USOS, and substantial solar arrays supplementing the station's existing 4 solar arrays. Over the next 2 years the station continued to expand. A Soyuz U rocket delivered the post-docking compartment. The space shuttles Discovery, Atlantis, and Endeavour delivered the Destiny Laboratory and Quest airlock, in addition to the station's main robot arm, the Canadarm2, and several more segments of the integrated truss structure. The expansion schedule was interrupted by the destruction of the Space Shuttle Columbia on STS-107 in 2003, with the resulting hiatus in the Space Shuttle program halting station assembly until the launch of Discovery on STS-114 in 2005. Assembly resumed with the arrival of Atlantis on STS-115, which delivered the station's second set of solar arrays. Several more truss segments and a third set of arrays were delivered on STS-116, STS-117, and STS-118. As a result of the major expansion of the station's power-generating capabilities, more pressurized modules could be accommodated, and the Harmony node and Columbus European Laboratory were added. These were followed shortly after by the first two components of KIBA. In March 2009, STS-119 completed the integrated truss structure with the installation of the fourth and final set of solar arrays. The final section of KIBA was delivered in July 2009 on STS-127, followed by the Russian Proton module. The third node, Tranquility, was delivered in February 2010 during STS-130 by the Space Shuttle Endeavour, alongside the cupola, closely followed in May 2010 by the penultimate Russian module, Rassvet. Rassvet was delivered by Space Shuttle Atlantis on STS-132 in exchange for the Russian Proton delivery of the Zarya module in 1998, which had been funded by the United States. The last pressurized module of the USOS, Leonardo, was brought to the station by Discovery on her final flight, STS-133, followed by the Alpha Magnetic Spectrometer on STS-134, delivered by Endeavour. As of June 2011, the station consisted of 15 pressurized modules and the integrated truss structure. Still to be launched are the Russian multipurpose laboratory module Norka and a number of external components, including the European robotic arm. Assembly is expected to be completed by April 2014, by which point the station will have a mass in excess of 400 tons. The gross mass of the station changes over time. The total launch mass of the modules on orbit is about 417,289 kg. The mass of experiments, spare parts, personal effects, crew, foodstuff, clothing, propellants, water supplies, gas supplies, docked spacecraft, and other items add to the total mass of the station. Hydrogen gas is constantly vented overboard by the oxygen generators. Station structure. The Islands is a third-generation modular space station. Modular stations can allow the mission to be changed over time and new modules can be added or removed from the existing structure, allowing greater flexibility. Below is a diagram of major station components. The blue areas are pressurized sections accessible by the crew without using spacesuits. The station's unpressurized superstructure is indicated in red. Other unpressurized components are yellow. Note that the Unity node joins directly to the Destiny laboratory. For clarity, they are shown apart. Pressurized modules, Zarya. Zarya, also known as the Functional Cargo Block or FGB, was the first module of the International Space Station to be launched. The FGB provided electrical power, storage, propulsion, and guidance to the ISS during the initial stage of assembly. With the launch and assembly in orbit of other modules with more specialized functionality, Zarya is now primarily used for storage, both inside the pressurized section and in the externally mounted fuel tanks. The Zarya is a descendant of the TKS spacecraft designed for the Soviet Salyut program. The name Zarya was given to the FGB because it signified the dawn of a new era of international cooperation in space. Although it was built by a Russian company, it is owned by the United States. Zarya weighs 19,300 kg, is 12.55 am long and 4.1 am wide, discounting solar arrays. Built from December 1994 to January 1998 in Russia at the Khrunikhov State Research and Production Space Center in Moscow, Zarya's control system was developed by the Khartron Corporation. Zarya was launched on November 20, 1998, on a Russian Proton rocket from Baikonur Cosmodrome Site 81 in Kazakhstan to a 400 km high orbit with a designed lifetime of at least 15 years. After Zarya reached orbit, STS-88 launched on December 4, 1998, to attach the Unity module. Although only designed to fly autonomously for 6 to 8 months, Zarya did so for almost 2 years due to delays with the Russian service module, Zvezda, which finally launched on July 12, 2000, and docked with Zarya on July 26 using the Russian Kurs docking system. Unity, or Node 1, is one of 3 nodes, or passive connecting modules, in the U.S. orbital segment of the station. It was the first U.S.-built component of the station to be launched. Cylindrical in shape, with 6 berthing locations facilitating connections to other modules, Unity was carried into orbit by Space Shuttle Endeavour as the primary cargo of STS-88 in 1998. Essential space station resources such as fluids, environmental control and life support systems, electrical and data systems are routed through Unity to supply work and living areas of the station. More than 50,000 mechanical items, 216 lines to carry fluids and gases, and 121 internal and external electrical cables using 6 miles of wire were installed in the Unity node. Unity is made of aluminum. Prior to its launch aboard Endeavour, conical pressurized mating adapters were attached to the aft and forward berthing mechanisms of Unity. Unity and the 2 mating adapters together weighed about 11,600 kg. The adapters allow the docking systems used by the Space Shuttle and by Russian modules to attach to the node's hatches and berthing mechanisms. Unity was carried into orbit as the primary cargo of the Space Shuttle Endeavour on STS-88, the first space shuttle mission dedicated to assembly of the station. On December 6, 1998, the STS-88 crew mated the aft berthing port of Unity with the forward hatch of the already orbiting Zarya module. Zvezda, also known as DOS-8 or Service Module or SM. It provides all of the station's critical systems. Its addition rendered the station permanently habitable for the first time, adding life support for up to 6 crew and living quarters for 2. Zvezda's DMSR computer handles guidance, navigation and control for the entire space station. A second computer which performs the same functions will be installed in the Nauka module, FGB-2. The hull of Zvezda was completed in February 1985, with major internal equipment installed by October 1986. The module was launched by a Proton K rocket from Site 81/23 at Baikonur, on July 12, 2000. Zvezda is at the rear of the station according to its normal direction of travel and orientation. Its engines are used to boost the station's orbit. Alternatively, Russian and European spacecraft can dock to Zvezda's aft port and use their engines to boost the station. Destiny is the primary research facility for United States payloads aboard the ISS. In 2011, NASA solicited proposals for a not-for-profit group to manage all American science on the station which does not relate to manned exploration. The module houses 24 international standard payload racks, some of which are used for environmental systems and crew daily living equipment. Destiny also serves as the mounting point for the station's truss structure. Quest is the only USOS airlock, and hosts spacewalks with both United States EMU and Russian Orlan spacesuits. It consists of 2 segments, the equipment lock, which stores spacesuits and equipment, and the crew lock, from which astronauts can exit into space. This module has a separately controlled atmosphere. Crew sleep in this module, breathing a low nitrogen mixture the night before scheduled EVAs, to avoid decompression sickness in the low-pressure suits. PAS and PWASK, PAS docking module, SO1 or DC1, and PWASK, also known as the Mini Research Module 2, fifth degree THN/TH to the first THN/NTH/TH micron TH/TH 3/4 TH squared TH degree NTH micron TH no NTH/TH/TH to the first TH 1/4 TH 3/4 THN florin TH no 2, or FUITHO2. PAS and PWASK are Russian airlock modules. Each of these modules have 2 identical hatches. An outward opening hatch on the Mir space station failed after it swung open too fast after unlatching, due to a small amount of air pressure remaining in the airlock. A different entry was used, and the hatch repaired. All EVA hatches on the ISS open inwards and are pressure sealing. PAS was used to store, service, and refurbish Russian Orlan suits and provided contingency entry for crew using the slightly bulkier American suits. The outermost docking ports on both airlocks allow docking of Soyuz and Progress spacecraft, and the automatic transfer of propellants to and from storage on the ROS. Harmony is the second of the station's node modules and the utility hub of the USOS. The module contains 4 racks that provide electrical power, bus electronic data, and acts as a central connecting point for several other components via its 6 common berthing mechanisms. The European Columbus and Japanese Kiba laboratories are permanently berthed to 2 of the radial ports, the other 2 can used for the HTV. American shuttle orbiters docked with the ISS via PMA-2, attached to the forward port. Tranquility is the third and last of the station's U.S. nodes. It contains an additional life support system to recycle wastewater for crew use and supplements oxygen generation. 3 of the 4 berthing locations are not used. 1 location has the cupola installed, and 1 has the docking port adapter installed. Columbus, the primary research facility for European payloads aboard the ISS, provides a generic laboratory as well as facilities specifically designed for biology, biomedical research and fluid physics. Several mounting locations are affixed to the exterior of the module, which provide power and data to external experiments such as the European Technology Exposure Facility, Solar Monitoring Observatory, Materials International Space Station Experiment, and Atomic Clock Ensemble in space. A number of expansions are planned for the module to study quantum physics and cosmology. ESA's development of technologies on all the main areas of life support has been ongoing for more than 20 years and have been used in modules such as Columbus and the ATV. The German Aerospace Center DLR manages ground control operations for Columbus and the ATV is controlled from the French CNES Toulouse Space Center. Kiba is the largest single ISS module. This laboratory is used to carry out research in space medicine, biology, Earth observations, materials production, biotechnology, communications research, and as facilities for growing plants and fish. During August 2011, an observatory mounted on Kiba, which utilizes the ISS's orbital motion to image the whole sky in the X-ray spectrum, detected for the first time the moment a star was swallowed by a black hole. The laboratory contains a total of 23 racks, including 10 experiment racks and has a dedicated airlock for experiments. In a shirt-leaves environment, crew attach an experiment to the sliding drawer within the airlock, close the inner, and then open the outer hatch. By extending the drawer and removing the experiment using the dedicated robotic arm, payloads are placed on the external platform. The process can be reversed and repeated quickly, allowing access to maintain external experiments without the delays caused by EVAs. A smaller pressurized module is attached to the top of Kiba, serving as a cargo bay. The dedicated interorbital communications system allows large amounts of data to be beamed from Kiba SICS, first to the Japanese Kodama satellite in geostationary orbit, then to Japanese ground stations. When a direct communication link is used, contact time between the ISS and a ground station is limited to approximately 10 minutes per visible pass. When Kodama relays data between an LEO spacecraft and a ground station, real-time communications are possible in 60% of the flight path of the spacecraft. Ground staff use telepresence robotics to conduct on-orbit research without crew intervention. Cupola is a 7-window observatory, used to view Earth and docking spacecraft. Its name derives from the Italian word cupola, which means dome. The cupola project was started by NASA and Boeing, but cancelled due to budget cuts. A barter agreement between NASA and the ESA resulted in the cupola's development being resumed in 1998 by the ESA. The module comes equipped with robotic workstations for operating the station's main robotic arm and shutters to protect its windows from damage caused by micrometeorites. It features 7 windows, with a 80-centimeter round window, the largest window on the station. The distinctive design has been compared to the turret of the fictitious Millennium Falcon from the motion picture Star Wars. The original prop lightsaber used by actor Mark Hamill as Luke Skywalker in the 1977 film was flown to the station in 2007. RASVIT, also known as the Mini Research Module 1 and formerly known as the Docking Cargo Module, is similar in design to the Mir docking module launched on STS-74 in 1995. RASVIT is primarily used for cargo storage and as a docking port for visiting spacecraft. It was flown to the ISS aboard NASA's Space Shuttle Atlantis on the STS-132 mission and connected in May 2010. RASVIT is the only Russian-owned module launched by NASA, to repay for the launch of Zaya, which is Russian-designed and built, but partially paid for by NASA. RASVIT was launched with the Russian Narka Laboratories experiments airlock temporarily attached to it, and spare parts for the European robotic arm. Leonardo Permanent Multipurpose Module is a storage module attached to the Unity node. The three NASA Space Shuttle MPLM cargo containers Leonardo, Raffaello and Donatello were built for NASA in Turin, Italy by Alcatel Alenia Space, now Thales Alenia Space. The MPLMs were provided to NASA's ISS program by Italy and are considered to be U.S. elements. In a bartered exchange for providing these containers, the U.S. gave Italy research time aboard the ISS out of the U.S. allotment in addition to that which Italy receives as a member of ESA. The Permanent Multipurpose Module was created by converting Leonardo into a module that could be permanently attached to the station. Scheduled Additional Modules, NORCA, also known as the Multipurpose Laboratory Module or FGB-2, is the major Russian laboratory module. It was scheduled to arrive at the station in 2014, docking to the port that was occupied by the PAS module. However, the date has been postponed to February 2017. Prior to the arrival of the Narka module, a Progress spacecraft was used to remove PAS from the station, deorbiting it to re-enter over the Pacific Ocean. NORCA contains an additional set of life support systems and attitude control. Originally it would have routed power from the single science and power platform, but that single module design changed over the first 10 years of the ISS mission, and the two science modules, which attach to NORCA via the Ozlovoy module, or Russian node, each incorporate their own large solar arrays to power Russian science experiments in the ROS. NORCA's mission has changed over time. During the mid-1990s, it was intended as a backup for the FGB, and later as a universal docking module. Its docking ports will be able to support automatic docking of both spacecraft, additional modules and fuel transfer. NORCA is a module in the 20-ton class and has its own engines. Smaller Russian modules such as PAS and Pwask were delivered by modified Progress spacecraft, however the larger modules, Zvezda, Zaya, and NORCA, are launched by Proton rockets. They are the only modules on the ISS that contain engines or navigation computers with star, sun and horizon sensors, to enable flight and station keeping. Russia plans to separate NORCA, along with the rest of the Russian orbital segment, before the ISS is deorbited, to form the OPSEK space station. Ozlovoy module. The Ozlovoy module, or node module, is a 4-ton ball-shaped module will support the docking of two scientific and power modules during the final stage of the station assembly and provide the Russian segment additional docking ports to receive Soyuz TMA and Progress M spacecraft. NM is to be incorporated into the ISS in 2014. It will be integrated with a special version of the Progress cargo ship and launched by a standard Soyuz rocket. The Progress would use its own propulsion and flight control system to deliver and dock the node module to the nadir docking port of the NORCA MLM FGB-2 module. One port is equipped with an active hybrid docking port, which enables docking with the MLM module. The remaining 5 ports are passive hybrids, enabling docking of Soyuz and Progress vehicles, as well as heavier modules and future spacecraft with modified docking systems. However, more importantly, the node module was conceived to serve as the only permanent element of the future Russian successor to the ISS, OPSEK. Equipped with 6 docking ports, The node module would serve as a single permanent core of the future station, with all other modules coming and going as their lifespan and mission required. This would be a progression beyond the ISS and Russia's modular Mir space station, which are in turn more advanced than early monolithic first-generation stations such as Skylab, and early Salyut and Almaz stations. Science Power Modules 1 and 2, Bigelow Expandable Activity Module. Bigelow Expandable Activity Module is part of a contract with Bigelow Aerospace to provide a Bigelow Expandable Activity Module, which is scheduled to arrive at the space station in 2015 for a 2-year technology demonstration. Beam is an inflatable module developed by Bigelow Aerospace that will be attached to the aft hatch of the portside Tranquility module of the International Space Station. During its 2-year test run, instruments will measure its structural integrity and leak rate, along with temperature and radiation levels. The hatch leading into the module will remain mostly closed except for periodic visits by space station crew members for inspections and data collection. Following the test run, the module will be detached and jettisoned from the station. Cancelled components. Several modules planned for the station have been cancelled over the course of the ISS program, whether for budgetary reasons, because the modules became unnecessary, or following a redesign of the station after the 2003 Columbia disaster. The U.S. Centrifuge Accommodations Module was intended to host science experiments in varying levels of artificial gravity. The U.S. Habitation Module would have served as the station's living quarters. Instead, the sleep stations are now spread throughout the station. The U.S. Interim Control Module and ISS Propulsion Module were intended to replace functions of Zvezda in case of a launch failure. The Russian Universal Docking Module, to which the cancelled Russian research modules and spacecraft would have docked. The Russian Science Power Platform would have provided the Russian orbital segment with a power supply independent of the ITS solar arrays, and 2 Russian research modules that were planned to be used for scientific research. Unpressurized elements. The islands features a large number of external components that do not require pressurization. The largest such component is the integrated truss structure, to which the station's main solar arrays and thermal radiators are mounted. The ITS consists of 10 separate segments forming a structure 108.5 am long. The station in its complete form has several smaller external components, such as the 6 robotic arms, the 3 external stowage platforms and 4 express logistics carriers. Whilst these platforms allow experiments to be deployed and conducted in the vacuum of space by providing electricity and processing experimental data locally, the platform's primary function is to store orbital replacement units. ORUs are spare parts that can be replaced when the item either passes its design life or fails. Examples of ORUs include pumps, storage tanks, antennas and battery units. Such units are replaced either by astronauts during EVA or by robotic arms. While spare parts were routinely transported to and from the station via Space Shuttle resupply missions, there was a heavy emphasis on ORU transport once the NASA shuttle approached retirement. Several shuttle missions were dedicated to the delivery of ORUs, including STS-129, STS-133 and STS-134. As of January 2011, only one other mode of transportation of ORUs had been utilized, the Japanese cargo vessel HTV-2, which delivered an FHRC and CTC-2 via its exposed pallet. There are also smaller exposure facilities mounted directly to laboratory modules. The JM exposed facility serves as an external port for the Japanese experiment module complex, and a facility on the European Columbus laboratory provides power and data connections for experiments such as the European Technology Exposure Facility and the Atomic Clock Ensemble in space. A remote sensing instrument, SAGE-3 ISS, is due to be delivered to the station in 2014 aboard a Dragon capsule, and the NICER experiment in 2016. The largest such scientific payload externally mounted to the ISS is the Alpha Magnetic Spectrometer, a particle physics experiment launched on STS-134 in May 2011, and mounted externally on the ITS. The AMS measures cosmic rays to look for evidence of dark matter and antimatter. Cranes and robotic arms. Canadarm2, the largest robotic arm on the ISS, has a mass of 1,800 kilograms and is used to dock and manipulate spacecraft and modules on the USOS, and hold crew members and equipment during EVAs. The ROS does not require spacecraft or modules to be manipulated, as all spacecraft and modules dock automatically, and may be discarded the same way. Crew use the two STLA cargo cranes during EVAs for moving crew and equipment around the ROS. Each STLA crane has a mass of 45 kg. The Russian and Japanese laboratories both have airlocks and robotic arms. The integrated truss structure serves as a base for the main remote manipulator system called the Mobile Servicing System. This consists of the Mobile Base System, the Canadarm2, and Dijkstra. Dijkstra is a 1,500 kg agile robotic manipulator with two arms which have 7 degrees of movement each, a torso which bends at the waist and rotates at the base, a tool holster, lights and video. Staff on Earth can operate Dijkstra via remote control, performing work without crew intervention. The MBS rolls along rails built into some of the ITS segments to allow the arm to reach all parts of the United States segment of the station. The MSS had its reach increased an orbiter boom sensor system in May 2011, used to inspect tiles on the NASA shuttle, and converted for permanent station use. To gain access to the extreme extents of the Russian segment, the crew also placed a power data grapple fixture to the fore-docking section of Zaya, so that the Canadarm2 may inchworm itself onto that point. The European robotic arm, which will service the Russian orbital segment, will be launched alongside of the multipurpose laboratory module in 2017. The Japanese experiment module's remote manipulator system, which services the JEM exposed facility, was launched on STS-124 and is attached to the JEM pressurized module. Comparison: the islands follows Salyut and Almaz series, Cosmos 557, Skylab, and Mir as the 11th space station launched, as the Genesis prototypes were never intended to be manned. Other examples of modular station projects include the Soviet-Russian Mir, Russian OPSEK, and the as-yet unfinished Chinese space station. The first space station, Salyut-1, and other one-piece or monolithic first-generation space stations, such as Salyut-2, 3, 4, 5, DOS-2, Cosmos 557, Almaz and NASA's Skylab stations were not designed for resupply. Generally, each crew had to depart the station to free the only docking port for the next crew to arrive. Skylab had more than one docking port but was not designed for resupply. Salyut 6 and 7 had more than one docking port and were designed to be resupplied routinely during crewed operation. Station systems, life support. The critical systems are the atmosphere control system, the water supply system, the food supply facilities, the sanitation and hygiene equipment, and fire detection and suppression equipment. The Russian orbital segment's life support systems are contained in the service modules VISDA. Some of these systems are supplemented by equipment in the USOS. The MLM Norca laboratory has a complete set of life support systems. Atmospheric control systems. The atmosphere on board the ISS is similar to the Earth's. Normal air pressure on the ISS is 101.3 kPa. The same as at sea level on Earth. An Earth-like atmosphere offers benefits for crew comfort, and is much safer than the alternative, a pure oxygen atmosphere, because of the increased risk of a fire such as that responsible for the deaths of the Apollo 1 crew. Earth-like atmospheric conditions have been maintained on all Russian and Soviet spacecraft. The electron system aboard Zvezda and a similar system in Destiny generate oxygen aboard the station. The crew has a backup option in the form of bottled oxygen and solid fuel oxygen generation canisters, a chemical oxygen generator system. Carbon dioxide is removed from the air by the Vozduk system in Zvezda. Other byproducts of human metabolism, such as methane from the intestines and ammonia from sweat, are removed by activated charcoal filters. Part of the ROS atmosphere control system is the oxygen supply. Triple redundancy is provided by the electron unit, solid fuel generators, and stored oxygen. The electron unit is the primary oxygen supply, O, 2 and H, Mir-2 are produced by electrolysis, with the H2 being vented overboard. The 1 kilowatt system uses approximately 1 liter of water per crew member per day from stored water from Earth, or water recycled from other systems. Mir was the first spacecraft to use recycled water for oxygen production. The secondary oxygen supply is provided by burning O2 producing Vicar cartridges. Each candle takes €20 minutes to decompose at 450 500 AA degrees Celsius, producing 600 liters of O2. This unit is manually operated. The U.S. orbital segment has redundant supplies of oxygen, from a pressurized storage tank on the Quest airlock module delivered in 2001, supplemented 10 years later by ESA-built advanced closed-loop system in the Tranquility module, which produces O2 by electrolyses. Hydrogen produced is combined with carbon dioxide from the cabin atmosphere and converted to water and methane. Power and thermal control. Double-sided solar, or photovoltaic arrays, provide electrical power for the ISS. These bifacial cells are more efficient and operate at a lower temperature than single-sided cells commonly used on Earth, by collecting sunlight on one side and light reflected off the Earth on the other. The Russian segment of the station, like the Space Shuttle and most spacecraft, uses 28-volt DC from 4 rotating solar arrays mounted on Zarya and Zvezda. The USOS uses 130-180 of VDC from the USOS PV array. Power is stabilized and distributed at 160 of VDC and converted to the user-required 124 of VDC. The higher distribution voltage allows smaller, lighter conductors, at the expense of crew safety. The ROS uses low voltage. The two station segments share power with converters. The USOS solar arrays are arranged as 4-wing pairs, with each wing producing nearly 32.8 kilowatt. These arrays normally track the Sun to maximize power generation. Each array is about 375 am to an area and 58 meters long. In the complete configuration, the solar arrays track the Sun by rotating the alpha gimbal once per orbit while the beta gimbal follows slower changes in the angle of the Sun to the orbital plane. The night glider mode aligns the solar arrays parallel to the ground at night to reduce the significant aerodynamic drag at the station's relatively low orbital altitude. The station uses rechargeable nickel-hydrogen batteries for continuous power during the 35 minutes of every 90-minute orbit that it is eclipsed by the Earth. The batteries are recharged on the day side of the Earth. They have a 6.5-year lifetime and will be regularly replaced over the anticipated 20-year life of the station. The station's large solar panels generate a high potential voltage difference between the station and the ionosphere. This could cause arcing through insulating surfaces and sputtering of conductive surfaces as ions are accelerated by the spacecraft plasma sheath. To mitigate this, plasma contactor units create current paths between the station and the ambient plasma field. The large amount of electrical power consumed by the station's systems and experiments is turned almost entirely into heat. The heat which can be dissipated through the walls of the station's modules is insufficient to keep the internal ambient temperature within comfortable, workable limits. Ammonia is continuously pumped through pipework throughout the station to collect heat, then into external radiators exposed to the cold of space, and back into the station. The International Space Station External Active Thermal Control System maintains an equilibrium when the ISS environment or heat loads exceed the capabilities of the passive thermal control system. Note elements of the PTCS are external surface materials, insulation such as MLI, or heat pipes. The EATCS provides heat rejection capabilities for all the U.S. pressurized modules, including the JM and COF as well as the main power distribution electronics of the SO, S1 and P1 trusses. The EATCS consists of two independent loops, both using mechanically pumped liquid ammonia in closed-loop circuits. The EATCS is capable of rejecting up to 70 kW, and provides a substantial upgrade in heat rejection capacity from the 14 kW capability of the early external active thermal control system via the early ammonia servicer, which was launched on STS-105 and installed onto the P6 truss. communications and computers. Radio communications provide telemetry and scientific data links between the station and mission control centers. Radio links are also used during rendezvous and docking procedures and for audio and video communication between crew members, flight controllers and family members. As a result, the ISS is equipped with internal and external communication systems used for different purposes. The Russian orbital segment communicates directly with the ground via the Lyra antenna mounted to Zvezda. The Lyra antenna also has the capability to use the Luch data relay satellite system. This system, used for communications with Mir, fell into disrepair during the 1990s, and as a result is no longer in use, although two new Luch satellites, Luch 5A and Luch 5B were launched in 2011 and 2012 respectively to restore the operational capability of the system. Another Russian communications system is the Voskhod-M, which enables internal telephone communications between Zvezda, Zya, Paz, Pulsk and the USOS, and also provides a VHF radio link to ground control centers via antennas on Zvezda's exterior. The U.S. orbital segment makes use of two separate radio links mounted in the Z1 truss structure, the S-band and Ku-band systems. These transmissions are routed via the United States Tracking and Data Relay Satellite System in geostationary orbit, which allows for almost continuous real-time communications with NASA's Mission Control Center in Houston. Data channels for the Canadarm2, European Columbus Laboratory and Japanese Kiba modules are routed via the S-band and Ku-band systems, although the European Data Relay System and a similar Japanese system will eventually complement the TDRSS in this role. Communications between modules are carried on an internal digital wireless network. UHF radio is used by astronauts and cosmonauts conducting EVAs. UHF is employed by other spacecraft that dock to or undock from the station, such as Soyuz, Progress, HTV, ATV and the Space Shuttle, to receive commands from mission control and ISS crew members. Automated spacecraft are fitted with their own communications equipment. The ATV uses a laser attached to the spacecraft and equipment attached to Zvezda, known as the proximity communications equipment, to accurately dock to the station. The Islands is equipped with approximately 100 IBM and Lenovo ThinkPad Model A31 and T61P laptop computers. Each computer is a commercial off-the-shelf purchase which is then modified for safety and operation, including updates to connectors, cooling and power to accommodate the station's 28V DC power system and weightless environment. Heat generated by the laptops does not rise, but stagnates surrounding the laptop, so additional forced ventilation is required. Laptops aboard the ISS are connected to the station's wireless LAN via Wi-Fi and to the ground via Ku-band. This provides speeds of 10 Mbps and 3 Mbps from the station, comparable to home DSL connection speeds. The operating system used for key station functions is the Debian version of Linux. The migration from Microsoft Windows was made in May 2013 for reasons of reliability, stability and flexibility. Station operations, expeditions and private flights. See also the list of International Space Station expeditions, space tourism, and the list of human space flights to the ISS. Each permanent crew is given an expedition number. Expeditions run up to 6 months, from launch until undocking. An increment covers the same time period, but includes cargo ships and all activities. Expeditions 1 to 6 consisted of 3-person crews, Expeditions 7 to 12 were reduced to the safe minimum of 2 following the destruction of the NASA shuttle Columbia. From Expedition 13 the crew gradually increased to 6 around 2010. With the arrival of the American commercial crew vehicles in the middle of the 2010s, expedition size may be increased to 7 crew members, the number ISS is designed for. Sergei Krikalev, member of Expedition 1 and commander of Expedition 11, has spent more time in space than anyone else, a total of 803 days and 9 hours and 39 minutes. His awards include the Order of Lenin, Hero of the Soviet Union, Hero of the Russian Federation, and 4 NASA medals. On August 16, 2005 at 1:44 a.m. EDT he passed the record of 748 days held by Sergei Avdyov, who had time-traveled 1/50th of a second into the future on board Mir. He participated in psychosocial experiment Sphinx 99, which examined intercultural and other stress factors affecting integration of crew in preparation for the ISS space flights. Commander Michael Fink has spent a total of 382 days in space, more than any other American astronaut. Travelers who pay for their own passage into space are termed spaceflight participants by Roscosmos and NASA, and are sometimes informally referred to as space tourists, a term they generally dislike. All 7 were transported to the ISS on Russian Soyuz spacecraft. When professional crews change over in numbers not divisible by the 3 seats in a Soyuz, and a short-stay crew member is not sent, the spare seat is sold by Mir Corp through Space Adventures. When the Space Shuttle retired in 2011, and the station's crew size was reduced to 6, space tourism was halted, as the partners relied on Russian transport seats for access to the station. Soyuz flight schedules increase after 2013, allowing 5 Soyuz flights with only 2 expeditions required. The remaining seats are sold for around $40 a million to members of the public who can pass a medical. ESA and NASA criticized private spaceflight at the beginning of the ISS, and NASA initially resisted training Dennis Tito, the first man to pay for his own passage to the ISS. Toyohiro Akiyama was flown to Mir for a week. He was classed as a business traveler, as his employer, Tokyo Broadcasting System, paid for his ticket, and he gave a daily TV broadcast from orbit. Anousheh Ansari became the first Iranian in space and the first self-funded woman to fly to the station. Officials reported that her education and experience make her much more than a tourist, and her performance in training had been excellent. Ansari herself dismisses the idea that she is a tourist. She did Russian and European studies involving medicine and microbiology during her 10-day stay. The documentary Space Tourists follows her journey to the station, where she fulfilled an age-old dream of man, to leave our planet as a normal persona, and travel into outer space. In the film, some Kazakhs are shown waiting in the middle of the steps for 4 rocket stages to literally fall from the sky. Filmmaker Christian Fry states filming the work of the Kazakh scrap metal collectors was anything but easy. The Russian authorities finally gave us a film permit in principle, but they imposed crippling preconditions on our activities. The real daily routine of the scrap metal collectors could definitely not be shown. Secret Service agents and military personnel dressed in overalls and helmets were willing to reenact their work for the cameras in an idealized way that officials in Moscow deemed to be presentable, but not at all how it takes place in reality. Spaceflight participant Richard Garriott placed a geocake aboard the ISS during his flight. This is currently the only non-terrestrial geocake in existence. Orbit. The islands is maintained in a nearly circular orbit with a minimum mean altitude of 330 km and a maximum of 410 km, in the center of the thermosphere, at an inclination of 51.6 degrees to Earth's equator, necessary to ensure that Russian Soyuz and Progress spacecraft launched from the Baikonur Cosmodrome may be safely launched to reach the station. Spent rocket stages must be dropped into uninhabited areas, and this limits the directions rockets can be launched from the spaceport. The orbital inclination chosen was also low enough to allow American Space Shuttles launched from Florida to reach the ISS. It travels at an average speed of 27,724 km per hour, and completes 15.50 in orbits per day. The station's altitude was allowed to fall around the time of each NASA shuttle mission. Orbital boost burns would generally be delayed until after the shuttle's departure. This allowed shuttle payloads to be lifted with the station's engines during the routine firings, rather than have the shuttle lift itself and the payload together to a higher orbit. This trade-off allowed heavier loads to be transferred to the station. After the retirement of the NASA shuttle, the nominal orbit of the space station was raised in altitude. Other, more frequent supply ships do not require this adjustment as they are substantially lighter vehicles. Orbital boosting can be performed by the station's 2 main engines on the Zvezda service module, or Russian or European spacecraft docked to Zvezda's aft port. The ATV has been designed with the possibility of adding a second docking port to its other end, allowing it to remain at the ISS and still allow other craft to dock and boost the station. It takes approximately 2 orbits for the boost to a higher altitude to be completed. In December 2008, NASA signed an agreement with the Ad Astra rocket company which may result in the testing on the ISS of a Vaccine plasma propulsion engine. This technology could allow station keeping to be done more economically than at present. The Russian orbital segment contains the station's engines and control bridge, which handles guidance, navigation and control for the entire station. Initially, Mir, the first module of the station, controlled the station until a short time after the Russian service module Zvezda docked and was transferred control. Zvezda contains the ESA-built DMS, a data management system. Using 2 fault-tolerant computers, Zvezda computes the station's position and orbital trajectory using redundant Earth horizon sensors, solar horizon sensors as well as sun and star trackers. The FTCs each contain 3 identical processing units working in parallel and provide advanced fault masking by majority voting. Zvezda uses gyroscopes and thrusters to turn itself around. Gyroscopes do not require propellant, rather they use electricity to store momentum in flywheels by turning in the opposite direction to the station's movement. The USOS has its own computer-controlled gyroscopes to handle the extra mass of that section. When gyroscopes saturate, reaching their maximum speed, thrusters are used to cancel out the stored momentum. During Expedition 10, an incorrect command was sent to the station's computer, using about 14 kilograms of propellant before the fault was noticed and fixed. When attitude control computers in the ROS and USOS fail to communicate properly, it can result in a rare force fight where the ROS GNC computer must ignore the USOS counterpart, which has no thrusters. When an ATV, NASA shuttle, or Soyuz is docked to the station, it can also be used to maintain station attitudes such as for troubleshooting. Shuttle control was used exclusively during installation of the S3 per second 4 truss, which provides electrical power and data interfaces for the station's electronics. Mission controls. The components of the ISS are operated and monitored by their respective space agencies at mission control centers across the globe, including Roscosmos's Mission Control Center at Kirilayov, Moscow Oblast, controls the Russian orbital segment which handles guidance, navigation and control for the entire station, in addition to individual Soyuz and Progress missions. ESA's ATV Control Center, at the Toulouse Space Center in Toulouse, France, controls flights of the unmanned European Automated Transfer Vehicle. JAXA's JM Control Center and HTV Control Center at Tsukuba Space Center in Tsukuba, Japan, are responsible for operating the Japanese Experiment Module Complex and all flights of the White Stork HTV cargo spacecraft, respectively. NASA's Mission Control Center at Lyndon B. Johnson Space Center in Houston, Texas, USA, serves as the primary control facility for the United States segment of the ISS and also controlled the Space Shuttle missions that visited the station. NASA's Payload Operations and Integration Center at Marshall Space Flight Center in Huntsville, Alabama, coordinates payload operations in the USOS. ESA's Columbus Control Center at the German Aerospace Center in Oberpfaffenhofen, Germany, manages the European Columbus Research Laboratory. CSA's MSS Control at St. Hubert, Quebec, Canada, controls and monitors the Mobile Servicing System, or Canadam-2. Repairs. Orbital replacement units are spare parts that can be readily replaced when a unit either passes its design life or fails. Examples of ORUs are pumps, storage tanks, controller boxes, antennas, and battery units. Some units can be replaced using robotic arms. Many are stored outside the station either on small pallets called express logistics carriers or share larger platforms called external stowage platforms which also hold science experiments. Both kinds of pallets have electricity as many parts which could be damaged by the cold of space require heating. The larger logistics carriers also have computer local area network connections and telemetry to connect experiments. A heavy emphasis on stocking the USOS with ORUs occurred around 2011, before the end of the NASA shuttle program, as its commercial replacements, Cygnus and Dragon, carry 1/10 to 1/4 the payload. Unexpected problems and failures have impacted the station's assembly timeline and work schedules, leading to periods of reduced capabilities and, in some cases, could have forced abandonment of the station for safety reasons, had these problems not been resolved. During Streets 120 in 2007, following the relocation of the P6 truss and solar arrays, it was noted during the redeployment of the array that it had become torn and was not deploying properly. An EVA was carried out by Scott Parazinski, assisted by Douglas Heerlock. The men took extra precautions to reduce the risk of electric shock, as the repairs were carried out with the solar array exposed to sunlight. The issues with the array were followed in the same year by problems with the starboard solar alpha rotary joint, which rotates the arrays on the starboard side of the station. Excessive vibration and high current spikes in the array drive motor were noted, resulting in a decision to substantially curtail motion of the starboard SARJ until the cause was understood. Inspections during EVAs on STS-120 and STS-123 showed extensive contamination from metallic shavings and debris in the large drive gear and confirmed damage to the large metallic race ring at the heart of the joint, and so the joint was locked to prevent further damage. Repairs to the joint were carried out during STS-126 with lubrication of both joints and the replacement of 11 out of 12 trundle bearings on the joint. 2009 saw damage to the S1 radiator, one of the components of the station's cooling system. The problem was first noticed in Soyuz imagery in September 2008, but was not thought to be serious. The imagery showed that the surface of one sub-panel has peeled back from the underlying central structure, possibly due to micrometeoroid or debris impact. It is also known that a service module thruster cover, jettisoned during an EVA in 2008, had struck the S1 radiator, but its effect, if any, has not been determined. On May 15, 2009, the damaged radiator panel's ammonia tubing was mechanically shut off from the rest of the cooling system by the computer-controlled closure of a valve. The same valve was used immediately afterwards to vent the ammonia from the damaged panel, eliminating the possibility of an ammonia leak from the cooling system via the damaged panel. Early on August 1, 2010, a failure in cooling looper, one of two external cooling loops, left the station with only half of its normal cooling capacity and zero redundancy in some systems. The problem appeared to be in the ammonia pump module that circulates the ammonia cooling fluid. Several subsystems, including 2 of the 4 CMGs, were shut down. Planned operations on the ISS were interrupted through a series of EVAs to address the cooling system issue. A first EVA on August 7, 2010, to replace the failed pump module, was not fully completed due to an ammonia leak in one of 4 quick disconnects. A second EVA on August 11 successfully removed the failed pump module. A third EVA was required to restore Loop A to normal functionality. The USSR's cooling system is largely built by the American company Boeing, which is also the manufacturer of the failed pump. An air leak from the USSR in 2004, the venting of fumes from an electron-oxygen generator in 2006, and the failure of the computers in the ROS in 2007 during STS-117 left the station without thruster, electron, FOSDUC and other environmental control system operations, the root cause of which was found to be condensation inside the electrical connectors leading to a short circuit. The 4 main bus switching units control the routing of power from the 4 solar array wings to the rest of the ISS. In late 2011, MBSU-1, while still routing power correctly, ceased responding to commands or sending data confirming its health, and was scheduled to be swapped out at the next available EVA. In each MBSU, 2 power channels feed 160 VDC from the arrays to 2 DC to DC power converters that supply the 124V power used in the station. A spare MBSU was already on board, but August 30, 2012 EVA failed to be completed when a bolt being tightened to finish installation of the spare unit jammed before electrical connection was secured. The loss of MBSU-1 limits the station to 75% of its normal power capacity, requiring minor limitations in normal operations until the problem can be addressed. As of September 2, 2012, a second EVA to tighten the bulky bolt, completing the installation of the replacement MBSU-1 in an attempt to restore full power, has been scheduled for Wednesday, yet in the meanwhile, a third solar array wing has gone offline due to some fault in that array's direct current switching unit or its associated system, further reducing ISS power to just 5 of the 8 solar array wings for the first time in several years. On September 5, 2012, in a second, 6HR EVA to replace MBSU-1, astronauts Sunita Williams and Akihiko Oshide successfully restored the ISS to 100% power. On December 24, 2013, astronauts made a rare Christmas Eve spacewalk, installing a new ammonia pump for the station's cooling system. The faulty cooling system had failed earlier in the month, halting many of the station's science experiments. Astronauts had to brave a mini blizzard of noxious ammonia while installing the new pump. It was only the second Christmas Eve spacewalk in NASA history. Fleet operations. Progress M23M was the 57th Progress spacecraft to arrive at the ISS, including Mir-2 and MSO-1 which installed modules. 35 flights of the retired NASA Space Shuttle were made to the station. TMA-13M is the 39th Soyuz flight, and there have been 4 European ATV, 4 Japanese Counetary White Stork, 4 SpaceX Dragon and 3 OSC Cygnus arrivals. Currently docked berthed, see also the list of professional crew, private travelers, both or just unmanned space flights. Scheduled launches and dockings berthings, all dates are UTC. Dates are the earliest possible dates and may change. Forward ports are at the front of the station according to its normal direction of travel and orientation. Aft is at the rear of the station, used by spacecraft boosting the station's orbit. Nadir is closest the Earth, zenith is on top. Uncrewed cargo ships are in light blue. Crewed spacecraft are in light green. Modules are white. Spacecraft operated by government agencies are indicated with GOV, while COM denotes those operated under commercial arrangements. Docking. All Russian manned spacecraft, modules, and Progress craft are able to rendezvous and dock to the space station without human intervention. Using Ker's radar they detect and intercept the ISS from over 200 kilometers away. The European ATV uses star sensors and GPS to determine its intercept course. When it catches up it then uses laser equipment to optically recognize VISDA, with Russian Ker's redundancy. Crews supervise these craft, but do not intervene except to send abort commands in emergencies. The Japanese HII transfer vehicle parks itself in progressively closer orbits to the station, and then awaits approach commands from the crew, until it is close enough for the crew to grapple it with a robotic arm and berth it to the USOS. The American Space Shuttle was manually docked, and on missions with a cargo container, the container would be berthed to the station with the use of manual robotic arms. Berthed craft can transfer international standard payload racks. Japanese spacecraft berth for 1 to 2 months. Russian and European supply craft can remain at the ISS for 6 months, allowing great flexibility in crew time for loading and unloading of supplies and trash. NASA shuttles could remain docked for 11–12 days. The American manual approach to docking allows greater initial flexibility and less complexity. The downside to this mode of operation is that each mission becomes unique and requires specialized training and planning, making the process more labor-intensive and expensive. The Russians pursued an automated methodology that used the crew in override or monitoring roles. Although the initial development costs were high, the system has become very reliable with standardizations that provide significant cost benefits in repetitive routine operations. An automated approach could allow assembly of modules orbiting other worlds prior to manned missions. Soyuz manned spacecraft for crew rotation also serve as lifeboats for emergency evacuation. They are replaced every 6 months and have been used once to remove excess crew after the Columbia disaster. Expeditions require, on average, 722 kg of supplies, and as of March 9, 2011, crews had consumed a total of around 22,000 meals. Soyuz crew rotation flights and progress resupply flights visit the station on average 2 and 3 times respectively each year, with the ATV and HTV planned to visit annually from 2010 onwards. Following retirement of the NASA shuttle Cygnus and Dragon were contracted to fly cargo to the station. From February 26, 2011 to March 7, 2011, 4 of the governmental partners had their spacecraft docked at the ISS, the only time this has happened to date. On May 25, 2012, SpaceX became the world's first privately held company to send a cargo load, via the Dragon spacecraft, to the International Space Station. Launching docking windows. Prior to a ship's docking to the ISS, navigation and attitude control is handed over to the ground control of the ship's country of origin. GNC is set to allow the station to drift in space, rather than fire its thrusters or turn using gyroscopes. The solar panels of the station are turned edge onto the incoming ships, so residue from its thrusters does not damage the cells. When a NASA shuttle docked to the station, other ships were grounded, as the carbon wingtips, cameras, windows, and instruments aboard the shuttle were at too much risk from damage from thruster residue from other ships' movements. Approximately 30% of NASA shuttle launch delays were caused by poor weather. Occasional priority was given to the Soyuz arrivals at the station where the Soyuz carried crew with time-critical cargo such as biological experiment materials, also causing shuttle delays. Departure of the NASA shuttle was often delayed or prioritized according to weather over its 2 landing sites. Whilst the Soyuz is capable of landing anywhere, anytime, its planned landing time and place is chosen to give consideration to helicopter pilots and ground recovery crew, to give acceptable flying weather and lighting conditions. Soyuz launches occur in adverse weather conditions, however the Cosmodrome had been shut down on occasions when buried by snowdrifts up to 6 meters in depth, hampering ground operations. Life aboard. Crew activities. A typical day for the crew begins with a wake-up at 6 o'clock, followed by post-sleep activities and a morning inspection of the station. The crew then eats breakfast and takes part in a daily planning conference with Mission Control before starting work at around 08:10. The first scheduled exercise of the day follows, after which the crew continues work until 13:05. Following a 1-hour lunch break, the afternoon consists of more exercise and work before the crew carries out its pre-sleep activities beginning at 19:30, including dinner and a crew conference. The scheduled sleep period begins at 21:30. In general, the crew works 10 hours per day on a weekday, and 5 hours on Saturdays, with the rest of the time their own for relaxation or work catch-up. The station provides crew quarters for each member of the expedition's crew, with 2 sleep stations in the Zvezda and 4 more installed in Harmony. The American quarters are private, approximately person-sized soundproof booths. The Russian crew quarters include a small window, but do not provide the same amount of ventilation or block the same amount of noise as their American counterparts. A crew member can sleep in a crew quarter in a tethered sleeping bag, listen to music, use a laptop, and store personal items in a large drawer in nets attached to the module's walls. The module also provides a reading lamp, a shelf and a desktop. Visiting crews have no allocated sleep module, and attach a sleeping bag to an available space on a wall. It is possible to sleep floating freely through the station, but this is generally avoided because of the possibility of bumping into sensitive equipment. It is important that crew accommodations be well ventilated. Otherwise, astronauts can wake up oxygen-deprived and gasping for air, because a bubble of their own exhaled carbon dioxide has formed around their heads. Food. Most of the food on board is vacuum-sealed in plastic bags. Cans are too heavy and expensive to transport, so there are not as many. The preserved food is generally not held in high regard by the crew, and when combined with the reduced sense of taste in a microgravity environment, a great deal of effort is made to make the food more palatable. More spices are used than in regular cooking, and the crew looks forward to the arrival of any ships from Earth, as they bring fresh fruit and vegetables with them. Care is taken that foods do not create crumbs. Sauces are often used to ensure station equipment is not contaminated. Each crew member has individual food packages and cooks them using the onboard galley. The galley features 2 food warmers, a refrigerator added in November 2008, and a water dispenser that provides both heated and unheated water. Drinks are provided in dehydrated powder form and are mixed with water before consumption. Drinks and soups are sipped from plastic bags with straws, while solid food is eaten with a knife and fork, which are attached to a tray with magnets to prevent them from floating away. Any food that does float away, including crumbs, must be collected to prevent it from clogging up the station's air filters and other equipment. Hygiene. Showers on space stations were introduced in the early 1970s on Skylab and Salyut 3. By Salyut 6, in the early 1980s, the crew complained of the complexity of showering in space, which was a monthly activity. The island does not feature a shower. Instead, crew members wash using a water jet and wet wipes, with soap dispensed from a toothpaste tube-like container. Crews are also provided with rinseless shampoo and edible toothpaste to save water. There are 2 space toilets on the ISS, both of Russian design, located in Zvezda and Tranquility. These waste and hygiene compartments use a fan-driven suction system similar to the Space Shuttle waste collection system. Astronauts first fasten themselves to the toilet seat, which is equipped with spring-loaded restraining bars to ensure a good seal. A lever operates a powerful fan and a suction hole slides open, the airstream carries the waste away. Solid waste is collected in individual bags which are stored in an aluminium container. Full containers are transferred to Progress spacecraft for disposal. Liquid waste is evacuated by a hose connected to the front of the toilet, with anatomically correct urine funnel adapters attached to the tube so both men and women can use the same toilet. Waste is collected and transferred to the water recovery system, where it is recycled back into drinking water. Crew health and safety. Radiation. The islands is partially protected from the space environment by the Earth's magnetic field. From an average distance of about 70,000 km, depending on solar activity, the magnetosphere begins to deflect solar wind around the Earth and ISS. However, solar flares are still a hazard to the crew, who may receive only a few minutes warning. The crew of Expedition 10 took shelter as a precaution in 2005 in a more heavily shielded part of the ROS designed for this purpose during the initial proton storm of an X-3 class solar flare, but without the limited protection of the Earth's magnetosphere, interplanetary manned missions are especially vulnerable. Subatomic charged particles, primarily protons from cosmic rays and solar wind, are normally absorbed by the Earth's atmosphere. When they interact in sufficient quantity, their effect becomes visible to the naked eye in a phenomenon called an aurora. Without the protection of the Earth's atmosphere, which absorbs this radiation, crews are exposed to about 1 millisievert each day, which is about the same as someone would get in a year on Earth from natural sources. This results in a higher risk of astronauts developing cancer. Radiation can penetrate living tissue, damage DNA, and cause damage to the chromosomes of lymphocytes. These cells are central to the immune system, and so any damage to them could contribute to the lowered immunity experienced by astronauts. Radiation has also been linked to a higher incidence of cataracts in astronauts. Protective shielding and protective drugs may lower the risks to an acceptable level. The radiation levels experienced on the ISS are about 5 times greater than those experienced by airline passengers and crew. The Earth's electromagnetic field provides almost the same level of protection against solar and other radiation in low Earth orbit as in the stratosphere. Airline passengers, however, experience this level of radiation for no more than 15 hours for the longest intercontinental flights. For example, on a 12-hour flight an airline passenger would experience 0.1 millisieverts of radiation, or a rate of 0.2 millisieverts per day. Only 1/5 the rate experienced by an astronaut in LEO. Stress. There has been considerable evidence that psychosocial stresses are among the most important impediments to optimal crew morale and performance. Cosmonaut Valery Ryumin wrote in his journal during a particularly difficult period on board the Salyut 6 space station, only all the conditions necessary for murder are met if you shut two men in a cabin measuring 18 feet by 20 and leave them together for 2 months. NASA's interest in psychological stress caused by space travel, initially studied when their manned missions began, was rekindled when astronauts joined cosmonauts on the Russian space station Mir. Common sources of stress in early American missions included maintaining high performance while under public scrutiny, as well as isolation from peers and family. The latter is still often a cause of stress on the ISS, such as when the mother of NASA astronaut Daniel Tanney died in a car accident, and when Michael Fink was forced to miss the birth of his second child. A study of the longest space flight concluded that the first 3 weeks represent a critical period where attention is adversely affected because of the demand to adjust to the extreme change of environment. While Skylab's 3 crews remain 1, 2, and 3 months respectively, long-term crews on Salyut 6, Salyut 7, and the ISS last about 5 to 6 months while Mir's expeditions often lasted longer. The island's working environment includes further stress caused by living and working in cramped conditions with people from very different cultures who speak a different language. First-generation space stations had crews who spoke a single language, while second- and third-generation stations have crew from many cultures who speak many languages. The island is unique because visitors are not classed automatically into host or guest categories as with previous stations and spacecraft, and may not suffer from feelings of isolation in the same way. Crew members with a military pilot background and those with an academic science background or teachers and politicians may have problems understanding each other's jargon and worldview. Medical effects of long-term weightlessness include muscle atrophy, deterioration of the skeleton, fluid redistribution, a slowing of the cardiovascular system, decreased production of red blood cells, balance disorders, and a weakening of the immune system. Lesser symptoms include loss of body mass, and puffiness of the face. Sleep is disturbed on the ISS regularly due to mission demands, such as incoming or departing ships. Sound levels in the station are unavoidably high. Because the atmosphere is unable to thermosiphon, fans are required at all times to allow processing of the atmosphere which would stagnate in the free-fall environment. To prevent some of these adverse physiological effects, the station is equipped with 2 treadmills, and the A-RED which enables various weightlifting exercises which add muscle but do nothing for bone density, and a stationary bicycle. Each astronaut spends at least 2 hours per day exercising on the equipment. Astronauts use bungee cords to strap themselves to the treadmill. Microbiological environmental hazards. Hazardous molds can develop aboard space stations that produce acids which degrade metal, glass and rubber. Threat of orbital debris. At the low altitudes at which the ISS orbits there are a variety of space debris, consisting of many different objects including entire spent rocket stages, defunct satellites, explosion fragments including materials from anti-satellite weapon tests, paint flakes, slag from solid rocket motors, and coolant released by USA nuclear-powered satellites. These objects, in addition to natural micrometeoroids, are a significant threat. Large objects could destroy the station, but are less of a threat as their orbits can be predicted. Objects too small to be detected by optical and radar instruments, from approximately 1 cm down to microscopic size, number in the trillions. Despite their small size, some of these objects are still a threat because of their kinetic energy and direction in relation to the station. Spacesuits of spacewalking crew could puncture, causing exposure to vacuum. The station's shields and structure are divided between the ROS and the USOS, with completely different designs. On the USOS, a thin aluminium sheet is held apart from the hull. The sheet causes objects to shatter into a cloud before hitting the hull, thereby spreading the energy of the impact. On the ROS, a carbon-plastic honeycomb screen is spaced from the hull, an aluminium honeycomb screen is spaced from that, with a screen vacuum thermal insulation covering, and glass cloth over the top. It is about 50% less likely to be punctured, and crew move to the ROS when the station is under threat. Punctures on the ROS would be contained within the panels which are 70 cm square. Space debris objects are tracked remotely from the ground, and the station crew can be notified. This allows for a debris avoidance maneuver to be conducted, which uses thrusters on the Russian orbital segment to alter the station's orbital altitude, avoiding the debris. Dams are not uncommon, taking place if computational models show the debris will approach within a certain threat distance. 8 dams had been performed prior to March 2009, the first 7 between October 1999 and May 2003. Usually the orbit is raised by 1 or 2 kilometers by means of an increase in orbital velocity of the order of 1 ams. Unusually there was a lowering of 1.7 km on August 27, 2008, the first such lowering for 8 years. There were 2 dams in 2009, on March 22 and July 17. If a threat from orbital debris is identified too late for a dam to be safely conducted, the station crew close all the hatches aboard the station and retreat into their Soyuz spacecraft, so that they would be able to evacuate in the event the station was seriously damaged by debris. This partial station evacuation has occurred on March 13, 2009, 28 June 2011 and 24 March 2012. Ballistic panels, also called micrometeorite shielding, are incorporated into the station to protect pressurized sections and critical systems. The type and thickness of these panels varies depending upon their predicted exposure to damage and of mission. According to a 2009 report, Space Corporation ENARJA is considering methods to remove from the station some modules of the Russian orbital segment when the end of mission is reached and use them as a basis for a new station, known as the Orbital Piloted Assembly and Experiment Complex. The modules under consideration for removal from the current ISS include the Multipurpose Laboratory Module, currently scheduled to be launched in 2017, with other Russian modules which are currently planned to be attached to the MLM afterwards. Neither the MLM nor any additional modules attached to it would have reached the end of their useful lives in 2016 or 2020. The report presents a statement from an unnamed Russian engineer who believes that, based on the experience from Mir, a 30-year life should be possible, except for micrometeorite damage, because the Russian modules have been built with on-orbit refurbishment in mind. According to the Outer Space Treaty, the United States and Russia are legally responsible for all modules they have launched. In Islands planning, NASA examined options including returning the station to Earth via shuttle missions as not designed for disassembly, and this would require at least 27 shuttle missions, natural orbital decay with random re-entry similar to Skylab, boosting the station to a higher altitude and a controlled targeted deorbit to a remote ocean area. The technical feasibility of a controlled targeted deorbit into a remote ocean was found to be possible only with Russia's assistance. The Russian Space Agency has experience from deorbiting the Salyut 4, 5, 6, 7 and Mir space stations, while NASA's first intentional controlled deorbit of a satellite occurred in 2000. As of late 2010, the preferred plan is to use a slightly modified Progress spacecraft to deorbit the ISS. This plan was seen as the simplest, most cost-efficient one with the highest margin. Skylab, the only space station built and launched entirely by the U.S., decayed from orbit slowly over 5 years, and no attempt was made to deorbit the station using a deorbital burn. Remains of Skylab hit populated areas of Esperance, Western Australia without injuries or loss of life. The Exploration Gateway platform, a discussion by NASA and Boeing at the end of 2011, suggested using leftover USOS hardware and Zvezda 2 feet, 6 as a refueling depot and servicing station located at one of the Earth-Moon Lagrange points, L1 or L2. While the entire USOS cannot be reused and will be discarded, some other Russian modules are planned to be reused. Nauka, the Node module, 2 science power platforms and Rassvet, launched between 2010 and 2015 and joined to the ROS may be separated to form OPSEK. The Nauka module of the ISS will be used in the station, whose main goal is supporting manned deep space exploration. OPSEK will orbit at a higher inclination of 71 degrees, allowing observation to and from all of the Russian Federation. On May 13, 2014, in response to U.S. sanctions against Russia over the conflict in Crimea, Russia's Deputy Prime Minister, Dmitry Rogozin, announced that Russia would reject a U.S. request to prolong the orbiting station's use beyond 2020, and would only supply rocket engines to the U.S. for non-military satellite launches. A proposed modification that would allow some of the ISS American and European segments to be reused would be to attach a Chinese-built EM drive and/or VASIM drive module to the vacated node with its own onboard power source, MGB-2/carbon nanotube superconducting electromagnetic shield generator and backup life support systems. This would permit the station to be moved to Mars orbit, arriving in late 2021 and serve as a staging post for future colonization. Additional smaller modules would also be needed at each end of the station to allow the field to be contiguous, and coils would also needed to be fitted along the length of the ISS in order to ensure adequate shielding. It would however allow long-term reliability testing of the concept for less cost than building a dedicated space station from scratch. Cost: the islands is arguably the most expensive single item ever constructed. As of 2010, the cost is estimated to be $150 a billion. It includes NASA's budget of $58.7 a billion for the station from 1985 to 2015, Russia's $12 a billion ISS budget, Europe's $5 a billion, Japan's $5 a billion, Canada's $2 a billion, and the cost of 36 shuttle flights to build the station. Estimated at $1.4 a billion each, or $50.4 a billion total. Assuming 20,000 person-days of use from 2000 to 2015 by 2 to 6 person crews, each person day would cost $7.5 a million, less than half the inflation-adjusted $19.6 a million per person day of Skylab. International cooperation. Participating countries. Sightings from Earth, naked eye. The islands is visible to the naked eye as a slow-moving, bright white dot due to reflected sunlight, and can be seen in the hours after sunset and before sunrise when the station remains sunlit but the ground and sky are dark. The islands takes about 10 minutes to move from one horizon to another, and will only be visible part of that time due to moving into or out of the Earth's shadow. Because of the size of its reflective surface area, the ISS is the brightest man-made object in the sky excluding flares, with an approximate maximum magnitude of 4 when overhead, similar to Venus. The islands, like many satellites including the Iridium constellation, can also produce flares of up to 8 or 16 times the brightness of Venus as sunlight glints off reflective surfaces. The islands is also visible during broad daylight conditions, albeit with a great deal more effort. Tools are provided by a number of websites such as Heavens Above as well as smartphone applications that use the known orbital data and the observer's longitude and latitude to predict when the ISS will be visible, where the station will appear to rise to the observer, the altitude above the horizon it will reach and the duration of the pass before the station disappears to the observer either by setting below the horizon or entering into Earth's shadow. In November 2012 NASA launched its Spot the Station service, which sends people text and email alerts when the station is due to fly above their town. The station is visible from 95% of the inhabited land on Earth, but is not visible from extreme northern or southern latitudes. Astrophotography, using a telescope-mounted camera to photograph the station is a popular hobby for astronomers, whilst using a mounted camera to photograph the Earth and stars is a popular hobby for crew. The use of a telescope or binoculars allows viewing of the ISS during daylight hours. Parisian engineer and astrophotographer Thierry Legault, known for his photos of spaceships crossing the Sun, traveled to Oman in 2011, to photograph the Sun, Moon and space station all lined up. Legault, who received the Marius Jaquemetin Award from the Société Copyright Astronomique de France in 1999, and other hobbyists, use websites that predict when the ISS will pass in front of the Sun or Moon and from what location those passes will be visible. See also: Center for the Advancement of Science in Spatial Euro operates the U.S. National Laboratory on the ISS. View. Notes. References. External links, Agency Islands websites. Research, NASA, Daily Islands Reports, NASA, Station Science, ESA, Columbus, RSC Naja, Science Research on ISS Russian Segment, Live Viewing. Live Islands webcam by NASA at Ustream TV, real-time position at heavens-above.com, real-time position at n2yo.com, real-time position at Hareth ISS at, multimedia, interactive reference guide at nasa.gov, image gallery search page at nasa.gov, assembly sequence animation by USA Today and NASA Islands tour with Sunita Williams by NASA at youtube.com, ISS tour with Andra copyright Coopers by ESA at youtube.com, The Future of Hope, Kibo module documentary by JAXA at youtube.com.